Hi, I'm April.
I'm David.
And I'm Kazen.
And this is our graphics final project. We chose to do our project in Three.js, with the main focus being creating custom scenes, unique lights, responsive camera movement, and custom shaders. The main scene was created in Blender, which you're seeing right now, using some free low-poly assets that we found online, which we then exported to Three.js to render the model. We then added a 2D sprite avatar as a way for users to move around the scene.
And this is the final product that we were able to come up with. Some of the features that we chose to implement include a custom scene in Blender, which you can see on screen here, and an animated 2D sprite. The camera will always follow the 2D sprite that's on screen, and you can press the spacebar to pan the camera up and down. Some of the post-processing effects that we implemented include our own custom bloom shader, which we'll showcase later, depth of field effects, shadows, and the particles you see on screen. And finally, as a way to showcase our multiple features, we implemented a day and night mode, which can be activated using the G button.
Thank you for listening to our final project, and we hope you enjoyed.
We wanted to showcase our results for advanced offline graphics, but since we were working off the Ray project, we could only generate static images. So, we first implemented object and camera movement along Bezier curves. By giving the camera or object a series of points, we can define a smooth path and explore scenes from different angles. Each time step, we generate corresponding camera and object transformations, which allows us to generate a sequence of consecutive frames that we can later combine into a single video file.
We implemented an alternative to ray tracing called ray marching, also known as sphere tracing. Unlike ray tracing, which involves analytically solving for the ray primitive intersections using implicit equations, ray marching is an iterative approach that approximates intersections. Similar to ray tracing, we cast rays through each pixel of the image, but instead of directly solving for the intersection point, we iteratively march or take steps along each ray until we're close enough to some surface in the scene. To determine the distance from some point to a surface in the scene, we had to adopt a different shape representation called signed distance functions, or SDFs. A SDF of a shape maps an input 3D point in space to its distance to the closest point on the surface. This means the surfaces we want to render live on the 0 level set of the SDF. While ray marching allows us to produce visually identical renderings as ray tracing, it also allows us to render shapes we couldn't before, namely objects whose implicit equations have no closed form solutions, like fractals.
In order to combine the shape SDFs together, we calculate an overall value for the current distance from any object to our ray marched point by simply getting the minimum of the shape SDF values. This gives us the closest object to our marched point, which will produce a result that matches the ray trace output. However, getting the minimum is not the only way we can calculate our current distance to any object. By using a smooth union, which is defined by a polynomial function of the shape SDFs, we can blend objects smoothly instead of defining a hard boundary between objects. The amount by which shapes are blended together depends on a blend factor, which is adjustable. However, the polynomial smooth union is only defined between two objects. In order to blend more than two objects together, we noticed by inspecting the polynomial function that a smooth merging is possible if we recursively apply the smooth union with the shape SDFs being sorted beforehand. With regards to the way we color these blended shapes, while one option is to take the color of the closest object, we also implement a color blending flag, which will blend the color recursively, roughly proportional to the object's distance from the ray marched point.
There are a ton of other fascinating fractals that we can render with ray marching, but the Mandelbox was one of our favorites. You can see an array of fascinating patterns along the side of the box, and it only gets better the closer we get.
Hey everyone, welcome to CG City. For our final project, we built a web-based infinite procedurally generated city using 3.js. So let's take a walk around a little bit and explore. We have some cars here, and they obey traffic systems. So here the light is red, so it's not moving. As soon as it changes, there we go. We can also change the weather, so we can make it rain. It's raining. Or we can make it snow. And if you like it here, you can walk around forever. We'll keep loading in more city for you to explore. For a brief explanation of how it works, we first started out with creating 3D models for all of our assets in Vectory, and then exported them so that we could load them in 3.js. We then created an n-by-n grid of city blocks. Each block is either a building or a ground asset, and used Perlin noise to randomly decide the type and height of each block, so that we can control how scattered the buildings are in our city. You can see here if I change the Perlin noise seed, we'll get a new city. We also added controls to adjust the parameters. To add traffic, we randomly place cars in the city with different colors, and update each car's position according to two basic rules. Each car will move forward only when a green light is in front of it. And each car will look ahead to see if a collision will happen, and slow down if necessary. For our weather effect, we generate 20,000 particles that fall slowly. Each particle is generated by the particle system, and is actually just a 2D plane with a corresponding texture map facing towards the camera. For the rain, the particles just fall straight down, but for the snowing effect, we maintain a slight side-to-side movement per particle that changes slightly over time. In first person, we also fake an infinite city effect. In reality, the camera never leaves the bounds of the original generated city, and if I turn off the effect, you can see that trying to leave just loops you over to the other side. So right now, there's nothing in front of us. We're reaching the edge of the city, and then we've teleported over to the other side. However, by creating copies of the city in front of you as you get close to the edge, you don't notice this looping. What looks like new terrain loading in is actually just you being teleported backwards. If you want to play around with this yourself, you can try it out with the link on our GitHub page. Thanks for watching.
We got a #1 victory royale. Yeah, Fortnite, we bout to get down. 10 kills on the board right now. Just wiped out Tomato Town. My friend just gone down. I revived him, now we're heading southbound. Now we're in the Pleasant Park streets. Look at the map, go to the marked sheet. Take me to your Xbox to play Fortnite today. You can take me Moisty Mire, but not Loot Lake. I really love to Chug Jug with you. We can be pro Fortnite gamers. He said, hey broski, you got some heals in the shield pot? I need healing and I am only at 1 HP. Hey dude, sorry, I found nothing on this safari. I checked the upstairs of that house, but not the underneath yet. There's a chest that's just down there. The storm is coming fast and you need heals to prepare. I've got V-Bucks that I'll spend, more than you can contend. I'm a cool pro Fortnite gamer. Cool pro Fortnite. Take me to your Xbox to play Fortnite today. You can take me Moisty Mire, but not Loot Lake. I really love to Chug Jug with you. We can be pro Fortnite gamers. La 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 la, yeah. La 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 la, yeah. La 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 la, yeah. Will you be my pro Fortnite gamer? Pro Fortnite gamer. Can we get a win this weekend? Take me to Loot Lake. Let's take the game mode and we can just go dominate. Let's hop in an ATK, take me to the zone. I'm running kind of low on mass, I need to break some stone. First in, all of crazy clothes. A renegade raider and he's probably a pro. I just shot my back, I turn back and I attack. I just got
I wouldn't be surprised if they have an
royale. A victory royale. Take me to your Xbox to play
And
Fortnite
banana, we're gonna have
today. You can take me to Mire, but not Loot Lake. I really love to Chug Jug with you. We can be pro Fortnite gamers.
Okay, yellow.
#1 victory royale. Yeah. 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 #1 victory royale. #1 victory royale. Yeah. Will you be my pro Fortnite gamer? Pro Fortnite game.
Hi, we're Cloud Computing Team. We love clouds. That's why we've built an optimized real-time volumetric cloud renderer that can draw us beautiful clouds on our own computer. Our renderer can generate diverse, fluffy cloud shapes using what's called the whirly noise. It supports realistic lighting effects such as forward scattering to give our clouds the iconic silver lining look. And finally, we also add a sky shader with an optical scattering model to create a more immersive environment. Volumetric rendering is an awesome technique for drawing things like cloud because they don't have a rigid shape. Instead, each point of the cloud has a local density value. To render our clouds, we shoot rays from our eyes and integrate over all the light samples C, weighted by the local density mu, and the transmittance term T. To approximate the light value C, we cast a secondary ray towards the sun and compute the attenuated sunlight. Now we know enough about volume rendering, we can use whirly noise to generate some clouds for us. We took a set of stratified samples in 3D and passed them in a compute shader. The compute shader then generates a 3D noise texture where each voxel uses the distance to its nearest sample point as the noise value. We also wrap the sample points around the volume boundary to make sure the texture tiles seamlessly. To generate more interesting cloud shapes, we layer multiple whirly noise of increasing frequencies in different channels of the texture. A second lower resolution noise map is used to add cloud details by eroding the base cloud shape. Here are some scary looking maps we use to produce realistic lighting effects for our clouds. We use Beer's law to simulate the exponential decay of the light energy and the Henning-Greenstein function to model light's tendency to scatter forward in the clouds. To produce dark edges around the cloud, we implemented the so-called powder correction of Beer's law by multiplying another exponential factor. With the above techniques, the clouds have more realistic forward scattering around the sun, as well as darker shadows near the boundaries. Now, enough about maths, let's look at some beautiful clouds floating in the sky.
We are Team Drowning in Tears of Joy. For our final project, we decided to make a stylized underwater scene which features height mapping, scrolling textures, displacement mapping, pixelation and outline shaders, rotating shapes, transparency, and texture mapping.
When we began our project, we set out to create a fun, aesthetically pleasing, pixelated scene similar to a sprite art style. During this project, we wanted to focus on exploring different post-processing techniques that extended the base framework provided by our real-time projects. We were also inspired by Evan Wallace's work with realistic water movement, so we decided to include water and fluid movement in our scene.
To achieve scrolling water with height variation, we implemented both displacement mapping and height mapping along with a water texture on a 3D plane. Height mapping was achieved by setting a shape's UV coordinates as a third layout attribute and creating a scrolling height displacement map, then sending them to the first vertex shader. We distort the position on the primitive based on this displacement at a certain UV coordinate. Displacement mapping used a scrolling displacement map to distort a scrolling water texture in the first fragment shader. We sent the UV coordinates from the vertex shader to the fragment shader, then mapped the new distorted texture to the UV coordinates of only the plane shape.
Next came our pixelation filter, which ended up being 2 separate fragment shaders with 2 post-processing passes. This was accomplished by applying Sobel outlining first using one FBO and applying pixelation afterwards with another. This helped us achieve shape definition under pixelation, which helps shapes to appear more prominent and polished within the scene. To successfully pass the render output of one FBO as a sampler 2D texture to another FBO, we implemented ping-pong FBOs that effectively bounce textures between 2 FBOs and their frame buffers before finally rendering the last post-process pass to our scene.
Finally, in addition to the custom scene file we created, the additional features we implemented were texture mapping using UV coordinates, transparency using alpha blending to achieve the look and feel of real water, as well as using time to manipulate angle of rotation and position of the cones in order to achieve our floating, rotating diamond. Thanks for watching!
This is Desktop World, an interactive scene built with 3.js showing an extraordinary world in a very ordinary room. Let's look at some of the features.
Our world, encompassed by a cone of light, features procedurally generated terrain stylized with our own custom shader material. We made use of height mapping to color different parts of the terrain and simplex noise with multiple octaves to generate interesting patterns. We also apply additional heuristics to make sure that the terrain levels out before it gets to the edge of the globe, as well as a radial distance metric to make sure all mesh vertices outside of the globe are never rendered.
If you look towards the top of the terrain, you can see a graceful flock of boids that follow with the drag of a mouse. Boids are spheres set to move with flocking patterns through weighted separation, alignment, and cohesion effects. We periodically cast rays into the scene and update the position of the boids to flock towards the mouse movement, as you can see here. We used to have collision detection as well, but found it was way too costly when running with more than 10 boids.
Procedurally generated cotton candy clouds send down a shower of rain, animated using particle effects and sprites. We use a simple state machine to determine whether it is raining or not, as well as how long a rain pattern would last. Down below, you can find water, represented by a plane with random sinusoidal vortex displacement. Along the edges, we added a white foam effect that is defined in our custom shader.
You look up into the sky and find floating islands filled with greenery and dreamy waterfalls. Our islands implement a number of geometric algorithms to sample, generate, and tessellate random polygon shapes, as well as smoothly join the top and bottom of each island. We use custom shaders and a particle system to create each waterfall.
It's lights off and bedtime. Just as you're about to sleep, your seemingly unremarkable globe begins to glow. Here we simulate bioluminescence using a bloom render pass, which is modified to selectively apply a radiant glowing effect to objects of our choosing. To selectively bloom objects, we traverse the scene and darken objects that are not meant to be bloomed while blooming others. Then, we restore the original material stored in the object map, limiting bloom to our tiny world. We have a set color profile for both bloom and non-bloom, and update the uniforms of all of our custom shaders accordingly to produce the color change.
Hope you enjoy!
Hey everyone, so for our final project, we created a procedurally generated city that we're really excited to share with all of you. Our first feature is the Bezier camera curve. So essentially this is just going to create a smooth path through the city streets just to show you around. There's some innate randomness, you can see it varying in the Y direction, but otherwise it's kind of just making this predetermined zigzagging path. We used a cubic Bezier curve, so that's 4 points that determine the path. And yeah, it's hopefully nice and smooth, and it'll just show you around the city.
Yeah, so one of the other things that we did to try to keep the city realistic was we created this varying building height that you can use to like change how tall the buildings are. Like as you can see, when I make it taller, it gets taller, and then the buildings like on average will get shorter if you toggle this lower because we're decreasing the max size. Zooming out, you can also see that, the building layout is totally random. We have, sometimes these buildings of varying heights and these clusters, but all of this changes with every like generation of the floor plan. So every time you reboot the program and also when you change building height, that's going to vary the floor plan too, as you can see.
Yeah, one other feature we had in our procedural city was the skybox, which is pretty apparent, as you can see. And if you just scroll around, it basically envelops the whole city with this box. And one slider we have actually is one that lets you toggle between day and night. So basically how this works is there's two different skybox textures that we're interpolating between linearly, and it creates the effect that the city is going through day and night cycles, which we thought was pretty cool. And another thing with how the skybox interacts with the city is there's also some directional lights we have set up to create some dark and lighter spots. And those are set up so, for example, the moon and the sun in the skybox textures align with those. So it looks like the sun is actually shining on the buildings.
And then the last feature is that we did texture mapping onto all of the buildings to give them textures. They're also buildings of different shapes and sizes. As you can see, the height is randomly generated, and Annika talked a little bit about the clusters and the buildings built together, but we have some kind of pentagonal buildings as well as more cubic dimensions that are all randomly chosen, and the textures mapped are also randomly chosen.
So yeah, that's kind of what we've worked on for our final project. And yeah, it's been really fun. So yeah, hope you guys enjoyed.
Our graphics final project was simulating fluid textures with procedurally generated height maps. The first step of our project was to generate a height map for the water. In order to do this, we procedurally generated Perlin noise with 4 octaves and a cubic easing function. We also adjusted its amplitude so that the noise was more useful for our purposes. The frequency of the noise, which will eventually become the frequency of waves in our water, can be controlled by parameter 1. Increasing parameter 1 increases the frequency and vice versa. In order to make the noise more wave-like, parameter 2 scales the noise in the x direction. Increasing parameter 2 makes the noise appear to stretch. We additionally implemented Worley noise generation as an alternative height map option. As with the Perlin noise, parameter 1 controls the frequency.
The next part of our project involves incorporating movement into our water. To do this, we use flow mapping, which requires flow map textures like those shown here. These flow map textures represent the vector telling where we want to change the UV coordinates. The R value of the flow map represents the change in the x direction, while the G value of the flow map represents the change in the y direction. Here we have a water texture image, and we increase the flow speed in order to show the change that the flow map applies to the image.
To apply the height map for water textures in the scene, we implemented bump mapping to perturb the surface normals of objects appropriately. Here we are applying an example bump map to the unit cube for demonstration. In terms of technical implementation, bump mapping required that we calculate a normal for each vertex in a shape in the tangent space, and then transform each of these normals into object, then world space. Here we show how this bump mapping can be applied to the water textures.
To have smooth camera movement, we implemented Bezier curves. Here is a demonstration of us traversing the curve on a sample file.
Putting all the parts together, here's a clip of our final product. This clip is showing how we can change the flow rate with the slider on our interface. This is just using a flow map that scrolls the water straight down. Here's that same flow map, but using a Bezier curve to control the camera.
Now to show what a few different flow maps look like, here's what a more swirling flow map looks like. The flow map is shown in the upper left-hand corner. The left hand shows the height maps generated using Perlin noise, and on the right hand side it's generated using Worley noise. Here's another flow map for demonstration. This one is more like a river-like flow. And on the left hand we have Perlin noise again, and on the right hand side we have Worley noise generating the height maps.
Itsy bitsy spider went up the water spout. Down came the rain and washed the spider out. Out came the sunshine and dried up all the rain. And itsy bitsy spider climbed up the spout again. Itsy bitsy spider went up the water spout. Down came the rain and washed the spider out. Out came the sunshine and dried up all the rain. And itsy bitsy spider climbed up the spout again. Itsy bitsy spider went up the water spout. Down came the rain and washed the spider out. Out came the sunshine and dried up all the rain. And itsy bitsy spider climbed up the spout again. Itsy bitsy spider went up the water spout. Down came the rain and
Hello everyone, my group and I have made a fun and interactable planet generator. Stepping through the features on the left hand side, we can tessellate a sphere all the way from 1 on both parameters back up to 500. We have found that the higher the tessellation, the higher resolution there is on our painted terrain. we have functionality for a skybox so that you can view your planet in a space-like setting. We also have a toggleable Phong shader or Toon shader. Phong we think looks a bit more realistic-esque, and Toon shader looks more cartoony and fun. And onto the brush side, the canvas at the right-hand side controls where terrain is painted onto the planet. So anywhere that green is drawn will be displacement mapped using a Perlin noise generator to be flatlands terrain, and you can see the bumpiness of the terrain easiest at the edge of the sphere at the bottom here. You can also draw mountains, so that you can have mountain ranges on your planet. And of course there's a selectable water brush so that you can add rivers or oceans or just erase any of the terrain that you've painted. The brush size is also scalable so that you can have large brushes and smaller brushes for fine details. We have also added functionality for saving your maps so that if you would like, you can save your maps to a file, and that way you can send them to other people, or save them for later use so that you can reload your old maps yourself. Here is a planet that is a bit impressionistic of what it would be like to paint Earth onto a sphere using our planet generator. And here is what it looks like to paint a crescent on our sphere.
Hi everyone, this is Ray Tracing Pet Better group. The members for this group are Khosro, Emre, and Amin. And for our final project, we decided to build a ray tracer using Vulkan. So let's talk about what Vulkan is.
So Vulkan is like API like OpenGL, and it's maintained by the same Chronos group. But Vulkan is better. NVIDIA is using it to do ray tracing on its RTX GPU series. And basically what we did is using the same technology, in a simpler way, to have real-time rendering, do ray tracing at the same time for the extra added effects. So we can hop into some samples.
So next tips or improvement. If we had more time, we would like to learn how to load MTL files, which can be used to add more complicated textures to our objects instead of what we use currently, which is image textures. We would like to add keyboard movement as we have done in the last project action. And we would like to make textures more accurate. If you noticed, like the plant didn't have the best texture possible, so we might want to improve that if we had more time. Credits, that's what everyone has done. Thank you for listening.
Hello, for our final project, we decided to develop an ocean basin animation, and you can see the following results. So our render involves 4 key features. The sand floor is given artificial depth through parallax occlusion mapping, which is built off of normal mapping. Our first result depicts procedurally generated waves, and our second is generated from a set of normal maps. Caustic rays project lighting refracted through the rays onto the seafloor, and finally we apply a deep sea filter using a frame buffer in post-processing. So the first feature is parallax occlusion mapping, which you can see on the seafloor. We used a quad render with the diffusion texture, and then generated normal textures and added normal maps along with displacement textures to give the artificial depth to the sand. And finally, we combined the normal and parallax mapping into the shader. Oh, sorry, you can skip it.
So as mentioned earlier, we had 2 different approaches for the ocean surface. The first one was using procedurally generated waves. So the ocean surface is composed of a set of trigonometric functions as shown by the formula on the screen here. And then the second approach was just using, sorry, next slide, please. Yeah, the second approach was just using normal maps where the normals of the ocean surface comes directly from the normal maps.
The caustic ray is a major feature to process water simulation. This feature is by enabling the OpenGL blend and render a virtual procedural generative wave, the same as top waves which lay on the ocean basin level. A ray is then casted in the set direction and has intersection with ocean basin plane. Result plane will be counted as a vertex of triangle strip and add light texture. The caustic ray consists 3 parts. First, compute the reflected ray, then compute the position where the ray hits the ground. Then compute the light intensity by checking the coverage.
After running the waves and sea basin and caustic ray, it's not really like the version in the deep. So we use the spectral absorption role of the seawater using the fine buffer to make an fragment shaders. We use the color map in fragment shaders like the equations we show on the right side, and what we get, then we get the result 1 as the picture shows. And practice mapping worked by me and Joy, and the caustic ray worked by Renhao and Yutong. And thank you guys for watching.
I'm Sebastian.
I'm Joel.
I'm Josh.
And we worked on this painting tree water simulation that you see here that's supposed to be like a little garden. So the main idea of the project was to create this painting that had a tree made with L systems that you can grow and customize. And then you also have like a pond scene in front of you that you can interact with, and we'll show you how you can do that in a second. So the first thing was the tree, which is the part I worked on. And so we start off with this little sapling, and you can increase the growth parameter to watch its life journey as it matures into a beautiful adult tree here. And you can adjust all these parameters. You can adjust the angle between branches. You can adjust the length of each segment. And you can adjust the thickness of each segment and how much it decays between each segment as well. And then you can also change like what generation of branching it's at. So like, since it's using L systems, we can control how many times it splits. And then another thing is at the terminal points, you can also add leaves, which is pretty, and you can also make them like shrink over time. Yeah, so that's, and then there are other parameters for making the tree more random. You can get some really wonky shapes and stuff. Yep. Josh, you want to talk about the water?
Yeah, so I was mainly in charge of the water, and as you can see, there's kind of like ambient ripples that occur every once in a while. And then we also have mouse interaction. So if you put the mouse over the water, it'll create like a ripple effect. And the water also rebounds along the edges of the pond for the waves. And then the other feature that we added was a little coin toss feature, where if you click the space bar, you can send a coin into the water and make a wish, and the coin gets tossed and is thrown to like a random spot in the pond. We were going to hook up a Venmo transfer, but we didn't get around to that, unfortunately.
And then,
all right, and finally, for styling the scene, we want to make it look like a painting. So we have like a paper look on it. I also did some cell shading on the tree as well as the sun to make it look tomb shaded. And I did like multiple render passes in order to outline the objects and also add noise for the paint-like effect, as you can see clearly on like the moon in the background.
Yeah. So this was our project. We hope you enjoyed. And yeah, we're just gonna make a pretty scene here.
Softblue is a soft body physics simulation with dynamic environment mapping and reflections.
And the features we implemented are firstly the icosphere and the icosphere subdivision.
And the soft body physics, for that we followed this paper which outlined using an icosphere as a spring mass system with the vertices as springs and vertices as masses and edges as springs. And whereas with a normal soft body simulation, you have tetrahedral meshes to simulate internal spring force. This paper outlines a new method where you can use the ideal gas law to find a pressure force on the normals of each vertex, kind of inflating it like a balloon.
And finally, we also implemented dynamic environment mapping. Environment mapping is implemented using the cube box as a surrounding texture, and the dynamic part comes from implementing the reflections by utilizing FBOs from 6 view angles.
So for this project, we wanted to create a manipulatable or customizable mesh that you could have your objects interact with. And so we'll see on the right, we currently have a clear terrain, and we could have just implemented a height map from another source, but we decided to combine previous projects with this idea of height maps. And so on the left of the screen here, we'll see that we can use a new height map based off of what we create on the canvas on the left. And we also decided that you could load in an image if you decided to import a more distinct height map. And so you'll see here that once we use this new height map, it will show up as a terrain on the right here.
Additionally, we are also able to move the camera along a defined path by Bezier curves. Once the camera position reaches a certain height, it will change direction to another Bezier curve path from the function. Eventually, the path can be defined with specific control points that are used to approximate the tangents of the other endpoints.
With the GPU ray tracer, I implemented the ray tracing algorithm similar to that we had been working on for projects 3 and 4 in a fragment shader. I did the bulk of my testing on spheres, and my code was able to implement any file from the scene files that we used on projects 3 through 6. Additionally, as my ray tracer was super fast on the GPU, I was able to navigate through scenes without really any lag and apply filters, as you can see me navigating around this scene. OpenGL doesn't allow for recursion, so all my reflections are iterative, and I also implemented shadows. After I got the GPU ray tracer working, I implemented the ray tracer on triangles to test my algorithm for ray intersections with the mesh. The algorithm does the ray intersect with the plane, and is it between the 3 points in the triangle. So this involved coming up with fake lighting and camera data to place in the scene, as well as some triangles. And as you can see, my triangles do ray trace and reflect. The struggle came, unfortunately, in connecting the mesh to the ray tracer. I worked for a whole day attempting to send a vertex array as a texture to the ray tracer. I tried both sampler 2D and sampler 1D and many different internal formats, but unfortunately the fragment shader was not picking up the array from the CPU, so I wasn't able to implement the mesh.
For future development, we can maneuver spherical objects around our complex mesh. By implementing the GJK algorithm, we can abstract detecting collisions from any convex shapes by generating simplexes. By calculating the Minkowski difference between vertices, the objects have collided if the resulting simplex contains the origin. The simplex will be built based on different dimensions of whether our current object hits a vertex, edge, or plane of the other object. Then, we can apply the EPA algorithm for collision responses between different object forces.
It'll be fun! Nope, not gonna do it. It's for the kids. Oh, okay. But they better not laugh. All right, better get on out there.
If you like to talk to tomatoes, if a squash can make you smile, if you like to waltz with potatoes, up and down the produce aisle, have we got a show for you. Broccoli, celery, gotta be vegetables.
Lima beans, collard greens, peachy keen,
Vegetables.
cauliflower, sweet and sour,
Hi, my name is Nicholas Vadas, and I'm a member of the final group W Systems. Our group project is generating novel crystal geometries with Perlin noise, ELF systems, and other computer science techniques. For our project, we limited our approach primarily to 3 categories of crystals, broadly described as trigonal crystals, cubic crystal systems, and Hopper crystals. Our approach begins with a central start point. From here, we developed 2 separate strategies. In one, we randomly generate vectors pointing out from this start point, sometimes bound to a specific hemisphere. In a separate approach, we can first generate a sheet of Perlin noise above our start point and pick random locations from this sheet, generating the normal from the direction of the start point to this selected endpoint, saving the distance between them for the next step. Once some number of normals are created, we may construct polygonal base points around this normal and feed them into a function that generates a crystal-like column given this base, as well as additional parameters that indicate things like height, whether the column narrows, whether it ends in a point or a plane, and so on. Another approach that we explored is to not start with a series of normals, but rather to generate a seed shape itself. This exists as a series of connected base points, for example hexagons, and the resultant columns can have parameters inherited from this seed shape. Controlling these parameters allows us to fine-tune our aesthetic output. At any point, we can start with an entirely new set of columns and parameters by regenerating our seed, a series of random values that's initially used as our parameters. We can save our geometry by either exporting it in the wavefront OBJ format or simply retrieving the numerical seed values that, when rendered, generate the current shape. We can see here that the main parameterized difference between quartz-like crystal clusters and cubic crystal systems is a mixture of flat-topped and fixed-width columns. For Hopper crystals, we take advantage of L systems that allow us to make a series of interconnected 2D lines. These go on to serve as a seed shape that we can scale on top of linearly in a predetermined growth direction. In future development, more sophisticated L systems could be used to generate not only the seed shape, but the staircase-like structure typical of Hopper crystals. Finally, after exporting our crystal geometries to the OBJ format, we can use Blender, Maya, or other 3D modeling softwares to showcase our shapes as beautiful renders.
As for the technical details, when the scene first loads, we have default textures and a BPM of 0 because there's no song. Once the BPM is set to a value based on the song loaded in, we start showing all the textures and animating based on those various parameters. So we have...
So we've got 4 variants. Oh yeah, nice, turn down. We've got 4 variants of mushroom, and they all move in different ways correlated with the BPM. We've got bouncing, swaying, color pulses, and rotating. And we also have the textured dance floor moving along with the BPM.
Nice. We've also got a post-processing pixel shader, which gives this nice effect of various amount of pixels. It just subdivides the image and renders that as squares. We also have a fog effect, which correlates with the far plane. So if you move it up, the far plane's closer, so you see less. If you move it away, you see more. And it just blends whatever the color set is on these RGB sliders with the color of, let me move it a little closer, with the color of the mushrooms, which is how you can change it there. And that's everything. Other than that, we have this animated pixel, which just animates this pixel parameter, and then some nice UI stuff to make it a little bit more user-friendly. But yeah, that's it.
Thanks for watching.
Should we do like a that's all, folks? Like a little loony.
Okay, nice.